I'm very honored to speak at this conference, and I'm very happy I was able to make it. So this work is based on collaboration with Anton Alexeyev, and the goal of this work, although I won't be able to say too much about it in this talk, is to associate twisted spin C structures to group value moment maps. Associate twisted spin C structures to group value moment maps. And the goal of that is to actually quantize group value moment maps in a certain sense. So let me recall that if you're quantizing ordinary moment maps in symplectic geometry, one way to proceed is using spin C Dirac operators. So you would start out by choosing a compatible almost complex structure, and you also suppose that you have a pre-quantization, and then you take the spin C Dirac operator with coefficients in the pre-quantum line bundle and take its equivariant index. That's then a G representation, or character of a G representation, and we take that to be our quantization. But for group value moment maps, that approach doesn't quite work. So typical examples for spaces with group value moment maps would be conjugacy classes, just like coadjuvant orbits are examples of ordinary moment map spaces. But there are examples of conjugacy classes of compact Lie groups that do not admit any spin C structure at all, so let alone compatible in whatever sense complex structure. So this approach doesn't work, and so you need something a bit more general. And this thing that's going to work are twisted spin C structures. So it turns out conjugacy classes of compact Lie groups actually carry canonical twisted spin C structures. Okay, so to get started, let me just define what is a spin C structure. Or rather give my preferred point of view towards spin C structures. Suppose you have any real vector bundle, a Euclidean vector bundle. Let me denote by Cliff B its Clifford bundle, so the complex Clifford bundle. So fiber-wise, that's the bundle of algebras with generators the element of your vector bundle and relations that v squared is length squared of v. And so that's the Clifford bundle. Then I can, and let's also assume for simplicity that our vector bundle has even rank. Then I can define a spin C structure as follows. So a spin C structure on V is given by a Z2 graded Hermitian vector bundle S, called the bundle of spinners, together with an isomorphism, with a star isomorphism. Of the Clifford bundle with endomorphisms of S. So that's one way of defining spin C structure. It's equivalent to the possibly more familiar way of defining spin C structures in terms of lift of the structure group. But this is better for my purposes. So the Z2 graded, I'm going to kind of sweep under the rug from now on. So a little bit of cheating will be necessary, just like in Anton's talk. Just to simplify the story a little bit. So some simple facts about spin C structure is that, first of all, there's an obstruction to the existence of spin C structures, which is this third integral Stiefel-Whitney class. And secondly, Well, here already I'm sweeping Z2 graded under the rug because there's another small abstraction having to do with Z2 grading. And secondly, if you have a spin C structure, then any other spin C structure is obtained by twisting with a line bundle. So any two are related by a line bundle. So in the sense that the new bundle of spinners would just be obtained by tensoring with a line bundle. And the line bundle can be recovered as bundle homomorphisms respecting the Clifford action from S to S prime. Okay, the simplest example of a spin C structure. Say if V is a symplectic vector bundle. You would choose a compatible complex structure. Then that splits the complexified vector bundle into V plus and V minus, plus and minus I eigenspaces of your complex structure. And then you have the bundle of spinners. This is a wedge of V plus. Also where the elements of V plus act by exterior multiplications and those of V minus act by contraction. That's a spin C structure. So that's one way of explaining why every symplectic vector bundle has a canonical spin C structure. Okay, so these Dix-May Dua-D bundles that I'm going to talk about, from now on I'm just going to say DD bundles. They are in a way generalizations of Clifford bundle. So the definition of a DD bundle is Dix-May Dua-D bundle. This is a bundle of star algebras well, Z2 graded, I should say, with typical fiber. The compact operators on a Hilbert space. Okay, let me recall compact operators on a Hilbert space. Are by definition the norm closure of the finite rank operators. So you take finite rank operators on a Hilbert space and then take its norm closure. So if your Hilbert space is finite dimensional, it's just the endomorphisms themselves. And if the Hilbert space is infinite dimensional, then you can say it's an appropriate version of infinite rank matrices. So it's, in a sense, norm limits are finite rank ones. I mean an ordinary Hilbert space, so separable complex Hilbert space. C infinity if you want. Okay, and then there's a notion of Morita trivialization, which is similar to spin C structure. A Morita trivialization of such a DD bundle. That's a Hilbert bundle of Hilbert spaces. To X, together with an isomorphism which identifies A with compact operators on that Hilbert space bundle. It's very similar. So it turns out there's an obstruction in general. The obstruction to existence of such a Morita trivialization is the Dix-May Dua-D class, the DD class. A certain class in H3. And secondly, if you have two Morita trivializations, they differ by line bundle. Also, E prime would be obtained as just tensoring with a line bundle. And again, you can recover the line bundle as bundle homomorphisms. Yes, you can go back and forth.
Excuse me, this abstraction, do you mean to say that it is a class which comes by reduction or from an integral class?
Which one?
Well, actually in both cases, because the Whitney classes are coefficients in Z2.
Yeah, these are the integral ones. Yeah, so this is the image on a box then of the class in H2 with.
To be this image.
Yeah, but this is the third integral Stiefel-Whitney class. That's how it's defined.
This should vanish.
Yeah, so this class vanishes if and only if there exists a spin C structure. And here's a class that vanishes if and only if there exists a Morita trivialization. And if it exists, then any two differ by a line bundle. Again, everything is Z2 graded, and then there's another small obstruction having to do with the Z2 grading, but I'll just ignore that. Okay, so as you can basically see from this picture, Clifford bundles are an example. So the example is, the first example is if A is a Clifford bundle. In which case the Dixmy duo D class is just this third integral Stiefel-Whitney class. And, well, Morita trivialization is just a spin C structure. Okay, so much for DD bundles. Actually, I need one more little generalization of this notion of Morita trivialization, which is the notion of Morita morphism. So more generally, you define Morita morphisms. Also, if you have two DD bundles, say over space X1 and X2, then I want to define morphisms of such things. And, well, it's given by an ordinary map of the underlying spaces, but not quite a map of the bundles. So instead, one has a bundle over X1, which is a bundle of bimodules. Also, one has E, then A1 acts from the right, and the pullback of A2 acts from the left. And should be such that it's modeled on compact operators on a Hilbert space H2, acting on compact operators from H1 to H2, just my multiplication from the right or left. So locally, the fibers should look like compact operators from one Hilbert space to the other Hilbert space. So the picture you can have in mind is that you have rectangular matrices. And these Morita morphisms, they allow you to change the size. Also, you might go from some infinite rank DD bundle to some finite rank one, for instance. Okay, so the DD theorem then says that the set of DD bundles up to Morita isomorphism, by which I mean Morita morphisms where the underlying map is just the identity map, that's classified by H3. So it's a higher rank version of line bundles, with Morita morphisms playing the role of line bundle isomorphisms. Okay, so that's what we need to know about DD bundles. Now let me get to Dirac structures. So in this talk, I'm going to need Dirac structures just in a linear algebra sense. There won't be any notions of integrability. I'll just talk about linear Dirac structures on a vector bundle. Okay, so Dirac structures. So the definition is a Dirac structure on a vector bundle is a Lagrangian, i.e. maximal isotropic, subbundle of the vector bundle which are obtained by doubling. So I take double V, which is V plus its dual. And this is Lagrangian relative to the natural symmetric bilinear form. So pairing of V1 alpha 1 with V2 alpha 2 would be, I think, 1/2 alpha 1 of V2 plus alpha 2 of V1. So that's all I mean by Dirac structure, no notions of integrability. So it's just very, very simple. So examples would be okay, let me denote the subbundle by E. And let me write such things by double V, so for this double vector space with the subbundle E. Then the basic examples would be you take your subbundle to just to be V. Because the bilinear form vanishes there and has the right dimension. Or you just take V star. Or you can take the graph of a bivector field. Bivector field. So view it as a map from V star to V. Or you can take the graph of a two-form. Those are all examples of Dirac structures. I will be more interested in Dirac structures that have to do with Lie groups. So the next example would be suppose you have any Lie algebra. And then we form this double, but for the tangent bundle of G star. So it's tangent bundle of G star plus the cotangent bundle of G star. And the Lagrangian subbundle we take to be, say it like this, it's spanned by sections. So it's going to have two components, a vector field component and a one-form component. And the vector field component are the generating vector fields for the coadjoint action. The one-form components are kind of the tautological one-forms one has, defined by any Lie algebra element xi. So that's also a Dirac structure. Actually, in a way, it's a special case of what we already have, because if you take, in this example, pi to be the Kirillov-Poisson structure, it's just a graph of the Kirillov-Poisson structure. So this is really the Kirillov Dirac structure, if you want. But it's a Poisson structure. Another example is if you take G to be a Lie group with symmetric bilinear form. On its Lie algebra. And again, we take this double tangent bundle, but this time of the Lie group. So tangent bundle plus cotangent bundle. Now there's a Dirac structure, denoted E sub G, which is spanned by, well, again, I take as a first component generating vector fields, but this time for the conjugation action. And for the second component, I take something along those lines. So I take 1/2 the left Maurer-Cattard form plus the right Maurer-Cattard form, inner product with psi. That's where I need my bilinear form. Again for psi and G. So this is called the Cartan-Dirac structure. Yes, invariant bilinear form. That's right. Yes, invariant and undegenerate. Anything else? It doesn't have to be positive definite necessarily. Right. But this is now an honest Dirac structure. It's not coming from a Poisson structure, or even from any bivector field. Okay, again, we need a notion of morphism. A notion of morphism of Dirac structures. The definition of morphism is a Dirac morphism So say we have V1, E1, and we want to map to V2, E2. It's given by two things. So it's given by a bundle map. From V1 and V2, together with two form. I suspect you've seen this in Marcus' talk, even though I wasn't able to attend Marcus' talk. Such that any element in E2 comes from a unique element in E1, in the sense that for all V2, alpha 2 in E2, there exists a unique element V1, alpha 1 in E1, such that V2 is the image of V1 and alpha 1 is the image of alpha 2 plus contraction of omega by V1. So that's a morphism of Dirac structures. In some contexts also known as morphism of Manin pairs. So these pairs are sometimes also called Manin pairs. And, well, here's some examples. If you have a Hamiltonian G-space in symplectic geometry, also with a two form and an ordinary moment map, that gives rise to a Morita morphism from the tangent bundle. Okay. So Hamiltonian G-space, a manifold, a two form, and an ordinary moment map. It gives rise to a morphism where the map is just a differential of phi, and the two form is the two form, and goes from Tm to Tg star with this Kirillov-Dirac structure. So you can actually define Hamiltonian G-spaces in this way, except that I haven't mentioned integrability. So you have to throw in the extra condition that d of omega is 0. But such a Dirac morphism together with d omega is equal to 0 is exactly the definition of a Hamiltonian G-space. Well, so this notion of Dirac morphism encodes everything. So that's one example. The other example is quasi-Hamiltonian G spaces. Well, it looks exactly the same. Except now the moment map takes values in the group. So I map to T of the group with this Cartan-Dirac structure. So as I mentioned, conjugacy classes would be an example. If M is a conjugacy class and the map's just inclusion. That's an example. Another example is also related to this Cartan-Dirac structures. There's a map G times G to G, which is just group multiplication. And you can take the differential of group multiplication with a certain 2 form, which I'm not going to write down. And this is then going to be a Dirac morphism TG TG times TG TG to TG TG. So in other words, the ordinary group multiplication lifts to a Dirac morphism. This 2 form, believe it or not, has something to do with the Kashiwara-Verne conjecture, but in a rather remote sense. So in our very first paper on Kashiwara-Verne, this 2 form entered. Okay. So our theorem is now.
Actually, can I ask a quick question?
Yes.
I was going to ask, is this associative? But first I should ask, can you compose Dirac morphisms?
Oh yeah, they can be composed.
Is it associative?
Yes. Mm-hmm. Yeah, I think I shouldn't write down now the formula for composition, but it's very easy, and you can probably invent it yourself. No, it's just very easy. Basically, you just compose the maps and you add the 2 forms, but 2 form you have to pull back. That's all. Okay, so our theorem now is that there's a functor I should put this in quotes. I have to do a little bit of cheating. It's more or less a functor from Dirac structures to DD bundles. So given a Dirac structure, I associate a certain DD bundle. And the point about this is really that it's a functor. So morphisms of Dirac structures go to morphisms of DD bundles, to go to Morita morphisms. Yes, over the same base. So this would be, say, over X, and this is again over X. And some of its main properties are that if your Dirac structure is just V, kind of the trivial Dirac structure, then you get A sub V, and it turns out, well, it's not equal, but it's Morita isomorphic to the Clifford bundle. And if you take your Dirac structure to be V dual, then the corresponding DD bundle is just Morita trivial. Okay, now let me, before I explain this a little bit, let me say how we apply this in our theories, why this is important, good for us. So really in those 3 examples. So if you have an ordinary Hamiltonian G space, we have this Dirac morphism. So we get a Morita morphism. So we get a Morita morphism from ATM to A of this EG star. But as I said, ATM, that's isomorphic to the Clifford bundle. Morita isomorphic to the Clifford bundle. And this guy, well, it's not quite the vertical Dirac structure, but it's the graph of bivector field. You can just scale the bivector field to 0 and then becomes vertical. And for that reason, the second fact shows you that it's Morita trivial. So you get a Morita morphism from the Clifford bundle to C, which is a spin C structure. So you get an ordinary spin C structure, and that's just the standard spin C structure. So we verified that this is the standard spin C structure. So this is for a Hamiltonian G space. Now for a quasi-Hamiltonian G space, well, it starts out the same way. The Clifford bundle is Morita isomorphic to ATM, and I get a Morita morphism to A sub G, so A sub EG, which now I'm going to denote A sub G, to this DD bundle over the group. But no, there's no longer any reason why this should be Morita trivial, and it's not. Okay? So this is what we would call the twisted spin C structure. Now, so there are two kind of remarkable things here. So first of all, there's this distinguished DD bundle over any compact Lie group, which is not trivial. And for a quasi-Hamiltonian G space, you get this distinguished Morita morphism from the Clifford bundle to this DD bundle over the group. So locally, you could, for instance, trivialize this DD bundle, and then locally you get spin C structures. But globally, those spin C structures wouldn't fit together. And so in that sense, it's twisted. And thirdly, this fact here shows that you get a kind of a multiplication map for this bundle over the group. Right? So this Dirac structure, it defines a DD bundle over the group, A sub G, and because of this multiplication morphism, this DD bundle over the group is multiplicative. So it just drops out from our theory. Yeah, I should maybe add one more thing here, just to explain this DD bundle over the group. So if you assume G is simple and simply connected, then one knows that H3 of the group is just the integers. And so you can ask, what is the DD class of this DD bundle under this isomorphism? So it turns out it's not the generator, but instead it's dual Coxeter number times the generator. So let's denote this generated by X. So this is the generator. And this is the dual Coxeter number. That's what this DD bundle is. Okay, and from this we see an interesting fact about quasi-Hamiltonian G spaces, so in particular for conjugacy classes, which is the fact that, so if you have a quasi-Hamiltonian G space, then the class of its Clifford bundle, which is this third integral Stiefel-Whitney class, is the dual Coxeter number times the pullback of the generator under the moment map. So this is a general fact about conjugacy classes, for example. If you take dual Coxeter number times the generator of H3, and you pull it back to a conjugacy class, you get the third integral Stiefel-Whitney class. You can see in this way whether it's been C or not.
Only the example you have is the extra transversality condition for the Dirac morphism, and they play no role in the Morita
Well, I kind of slip this in, that my Dirac morphisms are always strong. This we need in our construction somewhere. Any other questions? Oh yeah, G is supposed to be compact, simply connected. Or in this example here, G was supposed to be compact, yes. Thanks. Okay, so let me very briefly sketch how our construction goes. How we go from Dirac structures to DD bundles. So, brief sketch, brief outline of the proof of this theorem. Don't worry, it won't be so bad. So here's the outline, kind of the strategy of proof. So the way it works is we start off with some we start off with some Dirac structure. Then our first step is from the Dirac structure, we can construct some orthogonal transformation. So I'm just going to do the outline for x equals to a point. So V is just a vector space. So our construction is going to be really fiber-wise. So it's good enough to assume x is just a point. So we started with a Dirac structure. Then from that, we're going to construct an orthogonal transformation. Also, some orthogonal transformation of V. For this, I first have to pick some inner product on V. Okay. From the orthogonal transformation, we're going to construct a Scuit-John-Fredholm operator. D sub A. And from the Fredholm operator, well, so there's some Scuit-John operator on some infinite dimensional real Hilbert space. It's like a symplectic structure, except that it might have a kernel. But the Scuit-John-Fredholm operator gives rise to a polarization of this infinite dimensional real Hilbert space. Also, some J. But it's now an infinite dimensional real Hilbert space. And then from that polarization, well, the J gives rise to a spinor module, but now in infinite dimensions, and we take compact operators on that. And that's going to be our A. So I get to that. Polarization is basically an equivalence class of complex structures. Also, this is then a DD bundle. Or, well, yeah, DD bundle. Except this time it's over a point. Okay, let me explain in a bit more detail those 4 steps. So the first few steps are quite easy. So as I said, we start off by picking some inner product on V. So you pick an inner product on V. This is step 1. Pick an inner product B on V. Then we have the following picture. I mean, we have our vector space V plus V dual. And V and V dual are Lagrangian in that double. But we can choose different splitting of a vector space where we embed V kind of diagonally. And then there's another copy of V, but with minus the bilinear form. Also, on one copy, the bilinear form is going to be positive definite, on the other one is going to be negative definite. And now each Lagrangian subspace is going to be the graph of some map from V to V. And it turns out it's Lagrangian if and only if that map is orthogonal. Right, so in this way we get from any Lagrangian subspace to an orthogonal transformation. So that's the first step. So that's quite easy. The choice of bilinear form, choice of inner product doesn't really matter because any two are related by some deformation. That's not going to matter in the end. Okay, so step 2 is the skew-adjoint Fredholm operator. Well, it's also something rather easy. So what this d sub a is it's just the operator d by dt on the real Hilbert space, curly v, which is L2 functions on the interval with values in v. So these are the real valued L2 functions. Okay, but this is not really, so first of all, it doesn't seem to depend on A, and it's not really a skew-adjoint operator because it's not well defined. Right? I have to introduce some domain, I have to introduce boundary conditions. And that's really how A enters. So the domain of this are the L2 functions such that, first of all, f prime is L2, and now you use A to define boundary conditions. So f of 1 is minus A times f of 0. And so that's d sub A. So it's really a family of skew-adjoint Fredholm operators parametrized by orthogonal transformations. So one thing to note is, so as I said, skew-adjoint Fredholm operators, that's almost like a symplectic structure on this real Hilbert space, except that there might be a kernel. In this case, it's easy to figure out what the kernel is. Right? So d by dt of f being 0 means just f is constant. But then that constant has to satisfy those boundary conditions. So the kernel is isomorphic to just kernel of A plus identity as an operator on V. V embedded as constant functions. And if you go through our construction a little bit, you can see that this is also the same thing as E intersect V. So this Dirac structure intersect with the horizontal one. Okay, so in particular, the kernel is finite dimensional. But unfortunately, it might be non-zero. So if the kernel was 0, I could define a compatible complex structure. But the kernel might be non-zero. And so what I do is simply I perturb my operator a little bit. So you choose, so this is step 3, you choose a finite rank operator. On V, again skew-adjoint, such that d sub A plus Q is invertible. Okay, well, to do this, I would have to assume that the kernel is even-dimensional. So if the kernel is even-dimensional, I might just add some symplectic structure on the kernel. If the kernel is odd-dimensional, I just replace V by V plus R, and it's also not a big trouble. Okay, but if say, the kernel is even-dimensional, then I can clearly do this. I can make my operator invertible. And then I define a corresponding complex structure, which I may just write as, using functional calculus, d sub A plus Q divided by absolute value.
So this was micro-wise, but can this dimension jump when...
That's the point, yes. That's exactly the point. I can do this only fiber-wise, but I think I'll get back to this. So I can define a complex structure now. So this is an orthogonal complex structure on this infinite-dimensional real Hilbert space. But just as before, I can use it to define a spin C structure. Also, I can define an S sub j just wedge of V plus. Now I have to take a closure because I'm in infinite dimensions. Now, so with an action of the infinite dimensional Clifford algebra. Good. But now the tricky thing is, in infinite dimensions, the theory of spin representation is not as easy as in finite dimensions. So in infinite dimensions, the spin representation, it depends on the choice of complex structure in general. So what I've gotten here will depend on the choice of Q. But it turns out, and this is the key point about this whole construction is that it actually doesn't. So the fact is that S sub j is independent of Q up to isomorphism. Right, so if I make a different choice of Q, then the corresponding spinor modules are going to be isomorphic. Not canonically so, but the isomorphism is unique up to a scalar. So otherwise it's completely untrue. For example, if I change A, if I change the boundary conditions, then the spinor modules are going to be non-isomorphic. But it does not depend on the choice of Q. That's what we prove. And so what this implies is, since again, as I said, the isomorphism is unique up to a scalar, the compact operators on it are canonically defined. Really intrinsically. So Q doesn't matter at all. This is completely canonical. And that's our A. And that's the construction. So now, as you pointed out, if I make this bundle-wise, then this choice of Q I could only do locally. So that's the reason why this DD bundle in general is not Morita trivial. Yeah, and so that's the construction. Really, the harder part of our work is to make this construction compatible with morphisms. So to really cook up a way of making morphisms of Dirac structures into morphisms of DD bundles, into Morita morphisms. But I guess I won't have time to get into that, and so I'll just stop here.